Our dynamic universe. The key areas covered will be explosions and Newton's third law, conservation of momentum in explosions in one dimension only, kinetic energy in inelastic and elastic collisions. What we will do today is take notes and carry out calculations concerned with a variety of collisions and state what is meant by an elastic or inelastic collision. We will also use values for kinetic energy to determine if a collision is elastic or inelastic. Types of collision. When solving problems on types of collision, you first always need to make a sketch of the system before and after the collision or explosion. After this, you must mark all of the masses and velocities, including the direction, on this sketch. You will need to allocate a positive direction for vector quantities, mark this on the sketch as well. And 4, you need to use the rule, total momentum before equals total momentum afterwards. In general, there are 3 types of problem. The first type is when two masses collide and move apart with different velocities after the collision. Here we have 2 separate masses moving at 2 separate velocities beforehand, and after they're still 2 separate masses with 2 separate end velocities. We write this as m1u1 plus m2u2 equals m1v1 plus m2v2. The second scenario is when 2 masses collide and stick together. Here we have the 2 separate masses with 2 separate initial velocities, and after our 2 masses are combined, m1 plus m2, going at a final velocity. We write this as m1u1 plus m2u2 equals m1 plus m2 multiplied by v, where v is the velocity after the collision. The third scenario is explosions, using Newton's third law. In an explosion, one body, originally at rest, explodes into 2 parts moving in opposite directions. This follows Newton's third law. For every action, there is an equal but opposite reaction. Therefore, the momentum at the beginning is 0, so the momentum at the end must also be 0. Care must be taken to use negative values for any objects moving to the left to allow this law to hold true. Examples include a gun shooting a bullet and a cannon firing a cannonball. In this case, beforehand we have a mass and a velocity, and afterwards we have 2 separate masses with 2 separate end velocities. We write this as m1 plus m2 multiplied by v equals m1 multiplied by negative v1 plus m2 multiplied by v2. If initially at rest, for example, a gun before firing a bullet, then the left-hand side of the equation is equal to 0 because this initial velocity is 0. So 0 equals m1 multiplied by minus v1 plus m2 v2. A cannon of mass 2,000 kilograms fires a cannonball of mass 5 kilograms. The cannonball leaves the cannon with a speed of 50 meters per second. The speed of the cannon immediately after firing is, and this is what we want to work out. So let's first draw our diagram. So before, we have a cannon and a cannonball. That's a combined mass of 2,000 plus 5 kilograms. And this is travelling with a speed of 0. Afterwards, we have the cannon and the cannonball separately. So we've got 2,000 kilograms here, and we have 5 kilograms just here. The cannonball leaves the cannon with a speed of 50 meters per second, so we can add this 50 meters per second on, and we want to calculate the speed of the cannon after. So this side of the equation is going to equal 0 because our m1 v1 is going to be 0 because our v is 0. Therefore we have m1 v1 plus m2 v2 just there. So 0 is 2,000 times v1, then that's 5 times 50. So rearranging this, we have 2,000 v1 equals negative 250, and therefore our v1 is going to equal 0.125 meters per second, but as negative. So that's going to be moving to the left there. So 0.125 meters per second, this is answer A. Elastic and inelastic collisions. An elastic collision is one in which both kinetic energy and momentum are conserved. An inelastic collision is one in which only momentum is conserved. In any collision, all energy is conserved. Elastic and inelastic only deals with kinetic. During a space mission, it is necessary to dock a space probe of mass 4,000 kilograms onto a spaceship of mass 12,000 kilograms. The probe travels at 4 meters per second and the ship travels at 2 meters per second ahead of the probe, but in the same direction. What is the velocity of the ship after the probe has docked? Let's work on this first. Initially, we want to draw our diagrams. So before, we have the probe of mass 4,000 kilograms moving at a velocity of 4 meters per second. And we have the ship of 12,000 kilograms. Also moving forwards with a speed of 2 meters per second. Afterwards, the probe is docking to the ship, so we're going to have a combined mass of 4,000 plus 12,000 kilograms. And it's going to have an unknown velocity there. So we can write out our equation. We've got m1u1 plus m2u2, and that's going to equal m1 plus m2 multiplied by v. So we can substitute in our numbers here. 4,000 times 4 plus 12,000 times 2 equals 4,000 plus 12,000 multiplied by v. So we have 40,000 on the left-hand side. Oh, that's too many zeros there. Equals 16,000 v. And so our velocity is 2.5 meters per second. Because this is a positive number, we know that our spaceship and probe are still going to be moving to the right. Part B, is this collision elastic or inelastic? We know that for elastic and inelastic collisions, we need to work out the kinetic energy beforehand and afterwards to see if they match. So our kinetic energy before is going to equal a half mv squared, and we need to divide that up between the two ships. So we've got a half m1 u1 squared plus a half m2 u2 squared. So that's a half times 4,000 times 4 squared plus a half times 12,000 times 2 squared. Popping that all into a calculator gives us 56,000 joules. Let's calculate kinetic energy afterwards. So EK equals a half mv squared. Splitting this up, this is a half m1 plus m2 v squared. So we've got a half times 16,000, and we worked out our v to be 2.5, so we've got 2.5 squared in there, and that gives us an answer of 50,000 joules. We can see that our EK before is larger than our EK after, therefore it's an inelastic collision. Momentum can be measured in newtons per kilogram, newton meters per second, kilogram meters per second, or kilogram meters per second squared. This is a knowledge question, so we know that momentum can be measured in kilogram meters per second. If you're struggling to remember this, let's think back to our equation. Momentum equals mass times velocity. Mass is measured in kilograms, velocity is measured in meters per second. We can see that kilograms and meters per second directly add to give our momentum being measured in kilogram meters per second. A shell of mass 5 kilograms is travelling horizontally with a speed of 200 meters per second. It explodes into two parts. One part of mass 3 kilograms continues in the original direction with a speed of 100 meters per second. The other part also continues in this same direction. We want to work out its speed. So again, we want to draw our diagrams. So we have a shell of mass 5 kilograms, and it's travelling at 200 meters per second. And afterwards it splits into two, one part of 3 kilograms, and that's travelling at 100 meters per second. And then the other part we know to be 5 take 3, so we've got 2 kilograms, and that's travelling at an unknown speed. We want to work this out. So writing our equation, we've got mv equals m1 v1 plus m2 v2. In fact, if we replace that first v with a u, because we know it's an initial speed, so let's put our numbers in. We've got 5 times 200 is equal to 3 times 100 plus 2v. Therefore, we've got 1,000 equals 300 plus 2v2 there. Rearranging this gives v2 to equal 350 meters per second. This is an answer of D. A 2 kilogram trolley travels in a straight line towards a stationary 5 kilogram trolley as shown. The trolleys collide. After the collision, the trolleys move as shown below. What is the speed v of the 5 kilogram trolley after the collision? They've already drawn a few pictures for us, but to make sure we understand, we want to draw our own diagrams. So before, we've got a trolley of 2 kilograms moving at 4 meters per second, and we've got a trolley with a speed of 0 and a mass of 5 kilograms. After, we have the trolley of 2 kilograms is now moving to the left at 1 meter per second, and our trolley of 5 kilograms is moving to the right at a velocity of v that we don't know. So let's add in our equation here. We've got m1u1 plus m2u2 equals m1v1 plus m2v2. We know this m2u2 is going to equal 0 because our initial velocity there was 0. So we can say 2 times 4 equals 2 times 1 plus 5 times our unknown v2. So we've got 8 equals 2 plus 5v2. 5v2 equals, oh, can you see the mistake I've made just there? I should have put in a negative 1 just here because our block is moving to the left rather than to the right. So this should be a negative 2 just here. So our 5v2 is going to be 8 plus that 2, so we should have 10. Therefore, our v2 is going to be 2 meters per second to the right because it's positive. This is answer C there. This diagram shows the masses and velocities of 2 trolleys just before they collide on a level bench. After the collision, the trolleys move along the bench joined together. How much kinetic energy is lost in this collision? To work this out, we want to calculate the kinetic energy beforehand and the kinetic energy after the collision. But to calculate the kinetic energy after the collision, we need to know the velocity after the collision, so we need to work this out. First, let's draw our diagrams. So before, we have a trolley of 1 kilogram moving at 6 meters per second to the right, and a trolley of 2 kilograms moving at a speed of 0 meters per second. After, we have our trolleys joined together, so we've got a combined mass of 1 plus 2 kilograms moving at an unknown speed. So we have m1u1 plus m2u2 equals m1 plus m2 multiplied by v. Again, we know this m2u2 is going to equal 0 because our u2, our initial velocity, is going to be 0 for this, it's at rest. So we've got 1 times 6 is equal to 1 plus 2 times our v. Rearranging this, we get v equaling 2 meters per second. Now we can work out the kinetic energy before and after, for before the collision and after the collision. So our kinetic energy before is a half mv squared, which is going to be a half m1u1 plus a half m2u2. Oh, need to add the squareds on there. But again, for this second part of the equation is going to be 0 because our u2 is 0. So we've just got a half times 1 times 6 squared. So a half times 1 times 6 squared is going to equal 18 joules. Let's go for after now. Kinetic energy afterwards is a half mv squared. So we've got a half m1 plus m2 v squared, which is equal to a half times 3 times 2 squared, which is equal to 6 joules. To get the energy lost, we just need to do the 18, take away 6, so that is 12 joules. That is answer C. Two trolleys travel towards each other in a straight line along a frictionless surface. The trolleys collide. After the collision, the trolleys move as shown below. Which row in the table gives the total momentum and the total kinetic energy after the collision? To do this, we want to first draw our diagrams. So before, we have our 6 kilogram trolley travelling at 2 meters per second, and our 2 kilogram trolley travelling at 1 meter per second in the opposite direction. After, we have our 6 kilogram trolley travelling at 1 meter per second, and we have our 2 kilogram trolley travelling at an unknown speed. So we need to work out this unknown speed. So we have m1u1 plus m2u2 equals m1v1 plus m2v2. So 6 times 2 plus 2 times 1, but this 1 has to be negative because it's moving in the opposite direction. Then we've got 6 times 1 plus 2v2. Therefore we've got 12, take away 2 equals 6 plus 2v2. Rearranging this all to give v2, we get 2 meters per second. And because that's positive, we know it's moving to the right. Now we can calculate our total momentum after. That's going to be m1v1 plus m2v2. So we've got 6 times 1 plus 2 times 2. So we have 10 kilogram meters per second. We want our total kinetic energy afterwards as well. This is a half mv squared. Splitting this up, we've got a half m1v1 squared plus a half m2v2 squared. This is a half times 6 times 1 squared plus a half times 2 squared. Putting this all into a calculator, it gives us 7 joules. Let's have a look back to our table and see if we can find the matching row. We've got 10 kilogram meters per second, so that could be A, B or C, and we've got 7 joules, that could be A or E, so the row that matches both of these is answer A. A mass of 2 kilograms slides along a frictionless surface at 10 meters per second and collides with a stationary mass of 10 kilograms. After the collision, the 2 kilogram mass rebounds at 5 meters per second and the 10 kilogram mass moves off at 3 meters per second. Which row in the following table is correct? So similar to the last question, we want to work out the momentum of the system, kinetic energy of the system, and the type of collision. So because we've got a frictionless surface, therefore there'll be no kind of net external forces, the momentum of the system is going to be conserved. So we can already ignore D and E because that says the momentum is not conserved. We now want to figure out the kinetic energy of the system. To figure out if the kinetic energy is conserved, we want to work out the kinetic energy before and after the collision. So our kinetic energy before the collision is going to be EK equals a half mv squared, which is going to equal a half m1u1 squared plus a half m2u2 squared. So we've got a half times 2 times 10 squared. And this second section here is going to equal 0 because we've been told this block is at rest. So a half times 2 times 10 squared is 100 joules there. Now let's work out our kinetic energy after. So we've got EK equals a half mv squared, which is a half m1v1 squared plus a half m2v2 squared. This is a half times 2 times 5 squared plus a half times 10 times 3 squared. this is going to give us an answer of 70 joules. We can see that our kinetic energy beforehand is larger than our kinetic energy afterwards, so the energy has not been conserved, therefore the collision is inelastic. Let's have a look at our table to see if we can find any matching rows. So the kinetic energy of the system here, again, we can cancel out D and E, we talked about that before. EK not conserved, so we've got B and C just there. And we know this is an inelastic collision, we've got B just there. Our answer is B.